As I've been working to debug my 286 to 386 upgrade, I've run into an issue where to debug the 386 SX processor that I have to run minimally 2 megahertz on that processor. That, according to the spec, is the slowest I can run it. I didn't realize that. I thought a 386 SX, I thought they'd all be static, much like my 286, where I could pause the clock, stop the clock, run the clock at 5 hertz if I wanted to. But that apparently is not the case with the 386 SX. Now there is a 386 SXL and there's an SXLV that support fully static operation, but that's not the current processor I have. I do have a couple of the SXLs on order, so I should be able to at some point, once I get those in and build another 386 SX upgrade board, just assemble one, I should be able to run it at whatever speed I want to run it at. But I thought it might also be nice to be able to debug at faster speeds. You know, my current debugger that I put together really is based off of an Arduino Mega and some shift registers, and I don't think the Mega is really going to support the speed that I'm going to need to get to. And the main concern there is probably two things: the processing on the Mega that I'm doing to interpret the signals and, you know, some conditional logic and how to format it for output, things like that. But then also, how fast can I submit data from my Arduino Mega to the PC? And that's a USB serial, and it has a pretty significant speed limitation. Now I could step up to an Arduino Duo. I still will be on an Arduino. It is a faster processor. It does support USB transfer speeds instead of USB serial, so that would be a nice step up. However, at that point I do have to add voltage level shifters, and I thought, if I'm going to have to add voltage level shifters, why not just step up a little bit better than an Arduino? And so what you see here is my idea of what I'm considering, I guess, to order up here. And some of you do a lot of this, and so if you've got thoughts on how to improve this, let me know. But this is what I'm playing around with right now. Basically, for this, I'm looking to use an STM32. Specifically, it's a Nucleo H723Z8. And that board will sit on top of this PCB. It'll sit right here. And I don't actually have any specific mounting locations placed on this PCB, but I'll take care of that when I get it. I'll just use some standoffs and simply some adhesive to place those standoffs on this PCB, which works great. I do it all the time. But that's where this is going to sit. Now, this is a much faster processor. It has full USB transfer speed to the PC, I believe. And I'm not going to speak about this STM32 at all authoritatively, because I've just simply started to work with it and I have a lot to learn about it. And you're going to see that in the design of this, that I've really left the connectivity to that board open. Now what I do have here is my ISA signals coming in down here, and all the signals that I care about from the ISA bus I'm bringing up to these 8 shift registers that I have right here. So my address off the ISA bus, the data off the ISA bus, some of the control signals, things like that. And so those will come into these 8 shift registers. But there's other signals that I'm going to want to be able to get to. This is all stuff that would be either latched or going through a data transceiver before it gets onto the ISA bus. And at times I might want to debug the signals right off the processor, whether that is data or address or other types of unlatched control signals. So then up here, what I have is 96 more inputs, so I can grab, for example, A0 through A31 off of the bus on the side of the processor before it goes through any type of latching, or after the latches, I could grab all 32 address signals. Same with the data, and then I have another 32 for control signals or other types of input that I'd want to capture. And all of those are running through this series of shift registers that you see here. Now, one of the challenges with this STM32 board I'm using is knowing which pins are 5-volt tolerant. And I've done a little bit of reading on it, and it seems like there are pins that are 5-volt tolerant on this STM32, but not all of them. And I really don't feel like accidentally plugging a 5-volt in to a non 5-volt tolerant pin and wrecking this STM32. So I thought I'll just get everything converted to 3.3 volt. And so I have 3 voltage level shifters sitting right here. And so I have this dozen plus another 8 of these shift registers, the serial shift registers. So that gives me, 20 of those, 20 times, well, I'll just stop there, 20 of those. And each of those is going to have a single output that is serial. Well, that'll run through one of these. So I can now take between these 3 chips 24 signals, and I do need all 24, and I'll explain that in a second. But over here, then I would have 20 different serial outs running through these voltage level shifters that then go up to this set of headers up here. I'm not running them straight into the STM32. And the reason being is I don't know which pins I'm going to use. I don't know which pins support interrupts or DMA or anything else that I need to figure out how to work with that board. But I want to start working with this, and I don't want to have to figure all that out before I maybe get something that helps me connect stuff easier. And what you're seeing up here in this pin header here is I have, for example, all of these external inputs are coming through these dozen shift registers. And so then you're seeing that I have the first one through 8, and then I have 9 through 12. And then all of the internal stuff coming from the ISA bus, all of those shift registers, there's these 8, they each have their serial up here. So 1 through 4, 5 through 8. So then I have a few signals up here that have to do with loading the parallel data on the shift register and basically clocking in that data. So there's 3 pins that I'm going to use to control that. And then on top of that, I need to also pull in to this board whatever I'm going to use as the main clock source that I'm going to connect to interrupts on this board, the STM32 board. And that'll likely be my, on the 386SX, it'll be my peripheral clock or P clock. On the 386DX, it'll be the clock. Clock 2 is the double speed clock. Clock is what the processor runs at, as I understand it. So regardless, this will be the clock that's probably half of my overall system bus speed. So I have all of these shift registers. They're sending their final serial output through a voltage level shifter. All of that's coming up to this header, along with these 3 other signals that'll come out of this STM32. All these other signals will go into the STM32, and then I can, from that, control the shifting in. And I'll have to see if I do that through software shifting, or if there's a way to use the hardware shifting in this configuration where I have separate pins for each of the shift registers. Something else I considered was I could have one of these the output of one shift register go to the input of the next, and I believe I could chain these all together. Downside of that, a couple downsides is, one, if I wanted a signal off of just one chip, I didn't want everything. I would still have to shift in until I got to that bit, as I understand it. So that might not be optimal. Now the downside, the way I have it now, is for every one of these shift registers, I do have a separate pin that's got to go to this daughter board, this STM32 board. Anyways, that's how I've got it configured for now. And this is what I'm going to play with. So I think that should give me some pretty good options. And what I will do is connect from these pin headers into whatever pin on this board here itself. And it comes with headers already on on these here, and then these other ones I have to figure out. Are those just extensions or additional I/O that I can use, whatever those might be. And when I say 160 input, that's without any of these extra pins that are left unused after I connect up these 24 right here. So I'll have these 24. I've got to find 24 pins on here to use, but then whatever's left after that is still additional input that I could put into this. So I imagine actually I've got over probably 200 inputs that I should be able to manage. And I think the processor on the STM32 is going to be more than I need. If I go take a look at what else might be a bottleneck, the STM32, I believe, can run full USB speed into my PC, so I don't think that's going to be the bottleneck. if I take a look at the shift register, what I'm seeing for specs on that is that it's showing a maximum clock pulse frequency, at least for nominal temperature that I'm going to be working in at 4.5 volt. It shows a minimum clock speed supported of 27 megahertz. Now, I don't know how that's exactly going to translate to really how fast can I run this, but it seems like if I'm at 27 there, some of the other spec sheets I saw, maybe if I'm at 5 volt, I'm closer to 30 megahertz. But if I'm at, let's just say 27 megahertz, for me to pull in all of the bits off of one of these shift registers, I for sure have, 7 pulses to get the 8 bits plus the initial, loading and things like that. So let's just say I divide it by 10. Maybe I'm at this 2.7 megahertz that I could run at, and maybe that math is completely wrong, but that's kind of the assumption I'm going off of here is I should be able to support a 2 megahertz processor clock speed on my 286. The 386SX upgrade on my 286. I've not been able to yet to find what the minimum clock speed is on a normal 386DX. So if anybody does happen to know where that might be at, let me know. I did order up a 386DXL, and my assumption there is that again will be a version that I can run truly in a static mode. But that might be a bad assumption. And hopefully, though, if I can get to 2 megahertz here with the shift register, then I can go take a look over at the next piece that could be the bottleneck, which would be these level shifters. And if I look at the level shifters, I can see that they're listing this as 1.2 megabit for open drain and 110 megabit for push-pull. And I think I'm using push-pull, and this is something I suppose I would have to go understand things a bit more here, but and maybe that's not entirely true on some of the control signals. So some of those control signals I might not run in the same way. I'll have to figure that out as I get there, but I'm hoping that more of this is push-pull than it is open drain, and this is me just not understanding those signals well enough coming off of the specifically coming out of my 286 build. So I've got to do a little bit more research there, but I'm hoping that this 110 is more realistic of what I could do. And it seems like if they're single direction type signals, they're likely push-pull. Again, I could be wrong on that. But then anywhere I've got these pull up or pull downs, and I have multiple things that could modify it, I suppose those are the open drain ones. And that might then present me a problem. So we'll have to see how that plays out. Or if anybody has any feedback here, please let me know. So that's what I'm playing around with in my mind. And if that ends up being accurate as far as this push-pull for the most part, then I should be able to get some better speeds out of this. And I'll at least test it and see how fast can I go with it. If I am limited with open drain at 1.2 megabit, then that means that these level shifters will be a problem. And then I don't know what the workaround for that is. But looking for ideas. What would you do to make this better? If the goal is that I could run a 2 megahertz processor and at least be capturing the data and getting it to the PC at that speed, not writing it out to the screen on the PC, but at least getting it into memory so that I could record and then stop and then go back and be able to scroll through data or somehow report on that data that was captured. I think this is a pretty good step up from what I currently have for a debug card, but I'm sure I'm not thinking of other things that could be helpful here. So if you have ideas, let me know. Thanks.